So I'm Arnold Nipper, I'm from D6, and I want to give a presentation on building resilient, scalable Terabit Exchangepoints. Basically, what I want to tell about is how we restructured our infrastructure. That's all about it. It's not a theoretical talk, but it's really from experience how we managed to restructure our setup. So first I will motivate, and I will go through the design of our infrastructure, next is the implementation, and then how to scale the infrastructure, and at least I will do a summary. So this is D6, this is a Google picture from above. D6 is on what is an internet exchange point. Does everyone know what it is? No one knows. Okay, then I'll explain. Actually, what I understand on an internet exchange point is a metropolitan area infrastructure where BGP-capable speakers, I do not say ISPs, but BGP-capable speakers connect to an exchange traffic. So, I say it's metropolitan area because we do not want to have infrastructure connecting cities to each other. And I do not say ISPs because nowadays, what is an internet service provider? You can really not differentiate that way. It's too many types of service you can offer. And infrastructure, mainly this is related or means an Ethernet infrastructure. But this must not be only an Ethernet infrastructure. I guess the rest of the talk, if I talk of a switch, it means always an Ethernet switch, but it's not really confined to be an Ethernet switch. Maybe you can imagine something like a device with this switching wavelengths or something like that. Okay? So, coming back to that, this is what the D6 infrastructure from above looks like. This is where we started. Actually, that's not really true. We started here, but that's so long time ago that no one remembers but me. So actually, this is where it started, D6.1. Then we built D6.2 to have more resilience. Then third is, there was not only collocation over here, but also over there, and then we built the infrastructure D6.3 and D6.4. The next is, how did the topology look like? At every of these locations, we had switches, and they were connected somehow. And our goal was to really optimize these infrastructures, the way how the switches are interconnected. So this is how it looked like. So we had a main switch over here, D6.1, and all of the others were connected to this switch. And this switch had two functions. First, there were customers directly connected to that switch. On the other hand, as you can see from this topology, the straightforward lines, it also had the function to switch the traffic between all the other switches. Let's say a customer connected to here wants to talk to a customer connected to here. So there is no direct link in between. The only way is to go that way and then that way about. This is what not designed from scratch but grew over here. As I told, first it was D6.1, then we added another one, D6.2, and having two switches, there are not that much choices to interconnect. Then you just put in one link in between. The next step we really did is what these little boxes, these are so-called optical switches. So there is one link. In reality, these are link bundles coming in, and you have a working link, and then you have a backup link. And in course of failure of this device, actually, then this device is switching over to that device. Yes, correct. Both boxes are talking to each other, and that means In case this distribution device fails, we have a failover mechanism. And as I said, it's this D61 distribution switch has two functions. First, customer connections to it, and then it has a lot of backbone links. And it's really hard to manage to have enough ports left to extending the backbone and at the same time being able to connect more customers. And also, if this device fails, not only the customers or the backbone is affected, but also customers. And therefore, what we did almost 1 year ago, we said, okay, let's sit down and think about it, how we could optimize it. So first question we had to solve is which topology should we choose? There are a lot of topologies you can choose if you want to interconnect switches. If you want or do it a simple way with little amount of fibers or links in between, you typically would go for a ring infrastructure. That would mean you have all the switches interconnect just with two links, one going to the left side, the right side, and one going to the left side. This does minimize the number of interconnects of your infrastructure. On the other hand, that does not really optimize the way you have to shift traffic. If, for example, you have a lot of traffic between two switches which are not adjacent, then you have to route all the traffic through one switch. That means there is a lot of traffic going through a path which is not directly connected to the switch. The star topology is really appealing because it's very simple. You have something in the middle and everything connects just to this distribution point in the middle. Next question we had to solve which technology for interconnecting all these switches. We are not talking about just a single link, but we are meanwhile shipping hundreds of gigabits of traffic. Technology now is only at 10 gigabit. That means you have multiple links of 10 gigabit which you channel together through so-called Ethernet channels. You can do it by having or run simple dark fibers in between each switch, multiple simple dark fibers. There are more cost-efficient technology. This is DWDM. This means what you do, you have a single fiber and then you put devices on the end and you can inject traffic on one side and just transmit a single stream on a wavelength. And with nowadays technologies, this scales up to, let's say, 80 wavelengths. That means you have a single fiber and this has a capacity of 80 fibers there. The other is for resilience. If you think of the star topology, if the star in the middle fails, then everything is broken. No one is able to talk to each other. That means you have to put something in to have resilience. Typically, when you remember how switching works, the mechanism is a spanning tree. Spanning tree is, it cuts down all of the unnecessary link, on what is left is just a tree. And this tree infrastructure lays upon your topology. The drawback with the spanning tree is it does not use really a resilient infrastructure. That means if you have a ring topology, then there is at least one link which will not be used for traffic. There are other protocols like metal ring protocol, which is more or less, you can say, an improvement over SDP. And the last one is you put it down one layer to layer 0. You try to optimize or put the resilience into your fibers. remember the first picture, these fancy devices which we call fiber switches. It means you put down the task of having resilience in these fiber switches. Going through all these questions, we finally had the solution that we would like to go for star topology, but not simply have a single star, but have two switches using PW technology for interconnect. The main reason for that is, of course, because you save a lot of money for not have to have a lot of dark fibers, and also upgrading is very easy. You just have to put in new transceivers on both sides, and then you have another 10 gigs. Otherwise, if you do it with dark fiber, you first have to go to your carrier, say, okay, I want to have a new link between A and B, and then he says, let's say, it takes me 6 weeks, 10 weeks to provision that. And the last one is, we also went for layer 0 technology for resilience. Okay, now we come to the building blocks of the new infrastructure. These are the core switches. This is the middle of the star. Then the DWDM axis and the optical switches which do the resilience. So then, when it comes to this, the core switches are really crucial for your whole topology. So the question were, where do you really want to locate these core switches? Do you use the existing POPs? Do you create your own infrastructure and put the core switches there? And we have 4 POPs. Which POP do you choose for? And finally we came to the conclusion to take existing POPs. The main reason for that was cost efficiency. We had the infrastructure already in place, and we found out we will not really have additional resilience or improvement if we build our own POPs. It does not really add value to that. Because the infrastructure grows, there will be at least 1 more POP, or let's say 2 more POPs, more infrastructure you have to take care for. And if one fails, of course, what you will not do to put both cores in the same room. So look for as disjunct infrastructure as possible. Okay, next is, this is how the WDM infrastructure looks like. As said, we have dark fiber between the core and the access switch, and then you put in so-called DWDM, stands for Days Length Division Multiplexing, and then you can have as much, in this case up to 16 channels, which you may connect to the access switch, respectively to the core switch. Here we have a picture how these devices look like. This is completely passive infrastructure. That means you do not need any power. This is just using optical mechanism and a prisma mechanism. Everyone knows it. You have white light, it goes onto the prisma. On the other side, you have the whole rainbow of colors. Okay. So what we also did is we had one core switch was located over here in the interactive facilities, and the other core switch was located over there. And each access switch sitting here, 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 and here were connected by diverse fibers through the core. One of the fibers you see here, this is the Main River running that way, and one of the fibers running there. So this gives maximum resilience also fiber-wise. The next is what I call the layer 0 or optical switches. These are also small boxes. What you see, one fiber pair coming in and two going out. One is the working circuit and the other one is a protection circuit. And also what we try to do is to make it as simple as possible. These devices only need power in the case they have to switch from the working path to the protection path. In any other case, the fiber is latched in this position. Even if power fails, it stays here. And if power fails, of course, you are not able to switch anymore, but it works. As said, the primary and backup paths are going via diverse fiber routes. We also have master-slave mechanism to detect failures of one link in the fiber. Fiber always comes in two strands, one for transmit and one for receive. So we have also to install devices on both ends of the fiber to detect any case that something goes wrong. The next is to make all these devices which sit around every location what we have to talk to each other. This was really the hardest part, and we did it together with Lynx Networks, the manufacturer here of these devices. So in case of a failure, I go on to, yes, this is the optical protection, the access switch. See the access switch over here. You see the EWM, which maxes all these interfaces just into a single cable. And then you have the primary path going to core 0 and the X path going to the other core. And this optical switch, and you have this mechanism for all the access switches. And let's say this fails, then this one is signaling to all the other devices that something goes wrong and asks to switch over to the backup path.
So the signal on the backup link isn't there if the primary is working. So it's not 1+1 protection, but if the one fails, then it switches to the other. It does not send the signal on the backup all the time.
Actually, the full story is that 95% of the signal is going that way and 5% of the signal is going that way. Thus, to be sure that the backup path also is working. But there is not, what we do not do is to send 50% of the signal that way and 50% of the signal that way to do recombine. Was that the question you had?
And I was actually asking whether the signal was fully replicated all the time. So, like in 1+1 protection, so that 100% in the primary and 100% in the backup.
No.
So it's 95 in the primary and 5 in the backup.
It is also, there is no amplification or something like that. So that means you can only split the budget, but we do not amplify. Okay? And there is not really a need to amplify it or to have 100% that way and 100% that way. Because it
provides faster protection times. That is not that useful much. It will actually enable you to switch in 0 milliseconds.
Yes. I guess the problem is really with the infrastructure part. So you have to detect, so traffic is going that way and it's also coming back. So then the switches really would be irritating because every signal or every frame would be transmitted twice. You see? And I guess then you put the burden onto the switches, at least on the switches, or if you do not put it on the switches than on the end devices. Because with your proposition, what you do is every packet coming in here would be split, one going that way, one going that way. Leaving that to another access switch, and also leaving that going to the same access switch. So that, yes?
So how long does a failover take with those links boxes?
The links boxes is actually, they can switch over in 10 milliseconds.
What triggers this?
Excuse me?
What triggers this switchover?
The switchover may be triggered by a couple of events. Of course, one of the events is if you have a fiber cut over here, or with a single strand phase, because the slave device also detects both directions with this mechanism. Yeah, that's the only event, I guess. If this fails, there will be not a failover. If you have a cut in your fiber infrastructure.
But how is it detected? Because there are many ways.
What if only one lambda?
So these boxes monitored. If this is detected, so these boxes see no signal anymore.
No signal? What kind of signal?
These boxes are lambda
Optical.
unaware, right?
Optical
They are
signal.
lambda unaware, so if one lambda is...
Per lambda or per?
No, for the whole optical signal. So there's optical signal on it, and if this breaks, then this box detects there is no optical signal coming in at all. And then it's switching over.
But what if only one of these two numbers fail?
If only one of the numbers fails, then it will not switch over. There is also a mechanism that this is not really a 0-1 switching. You can also tell this box, please do a failover if, let's say, the signal is degraded by 10% or 20%. Yes. You will not detect if just, let's say, it's receiver phase or something.
You say that the optical switch is a passive, right? The power is only for switching.
Yes.
But if you say, let's monitor the level of the signal and
Yeah.
switch after losing 20%, it has to be active device. Because otherwise,
Yeah. It is active device in that sense that it has it monitors the signal, and if you have a power loss, you are not
it's still
anymore
working
able.
as before. It's all like keeping state before power.
Yes.
Power off.
Yes.
That's it. Okay.
That's it. There's other technology like MEMS which use power to also keep the mirror in some position.
Yeah.
You see?
So this is something.
And you can also trigger the failover.
You can also log into these boxes and say, please do a failover. Yeah. Okay.
What do you do when the optical switch master unit fails?
If the optical switch fails, yeah, then you exchange these optical switches.
The failover is in 10 milliseconds still or not?
If this device fails, then you have to exchange it.
Yeah, I mean,
That's simply.
there's no resiliency against it.
Now, what you could do is actually, if you say, okay, I'm not a friend of having a single point of failure, is you would just double it, and then you would lease half of your bandwidth. That would mean, let's say you need 40 gigabits here, then you would build a channel of 80 gigabits, just double your infrastructure and put in two devices.
But you don't do this.
No.
But Arnold, the thing is, even if this device fails, it doesn't need power to pass the light on, so it still stays in that state.
Yeah,
Continue
I guess
It's hard to
Integrate
imagine
it,
what
it would
the
really
need
is.
to stop the traffic.
Right.
Okay.
Yeah.
So they cannot fail.
Except burning or flood or disasters like this.
What may happen that if, for example, did a failover and for whatever reason it did stop just in the middle or whatever. It failed.
All I'm saying is, to his question, even if it fails, it continues forwarding, and yes, okay, of course you need to replace it, but up till then, it doesn't disturb the network.
I guess the question is really if it's completely failed, it's not doing what it's intended for, either put the line in this direction or that direction, right?
No, he's actually right. So it cannot.
Probably it's so low that you can skip this.
Of course, it can fail somehow. Nothing which is built by man cannot fail. So I guess this illusion is gone years ago.
But power outages.
Yes, but even a power outage does not really affect, other than you cannot do a switch. Okay. Okay. So this is the whole picture. This is the working state as said. Now we have just to make it more clear, left out all the optical devices. Every switch, edge switch, is connected to the core in both ways. And I guess we already run through it. If some of the fiber breaks, then you just switch over your edges to the standby port. And Elisa was asking how long it takes for the optical switch to switch over. It's 10 milliseconds. But what we also have is the signal goes away for a little amount of time. And this causes the interfaces also to go down for it goes down and comes up immediately. But what really would be ideal to have some sort of optical capacitor, you know.
But normally the layer 3 devices are able to not react immediately. So say if the interface goes down, even switches, if the interface goes down, then the customer will stay down by half second to detect that this is down.
Just hold on a second. The layer 3 devices are connected here. There is no layer 3 device. What you would see is perhaps if you really would have a close look, that traffic might stop for a millisecond or so, or 10 milliseconds or whatever.
Members sessions flat?
Members no, they do not. Because the backbone interfaces are going down and coming up.
Do you advise them to consider some sort of full timer or?
There is no need because members are connected here. Members interfaces are not going down at that time because no one of the member interfaces is connected to the optical infrastructure, only the backbone. And the channel is only going down, and you see almost in the same second it's coming back again.
And this is all the way up to the
yeah. So then, of course, theoretically, traffic must stop in between because you cannot transmit. But what we have seen, we did ping measures, we see the ping going up a little bit.
In the 10 milliseconds, then maybe traffic can be buffered at 10 milliseconds.
Yes, traffic will actually be buffered by device. Yes, but it's also in the time it's switched over, perhaps some information may be lost.
Did this actually happen? I mean, the switch over?
Yes.
Were not caused by you, but by some accident?
Not by some accident so
By
far.
some failure? I don't know.
Not by some accident so far. But what we decided is, if you have such an infrastructure in place, you want to see if it works. So what we decided to do is to test it each quarter, at least to say, does it really work? Does it really work? And this outage is only in the order less than a second, and it's acceptable for our users. So it does not break any BGP session. Yes? And therefore, every quarter we will switch over. Okay, now I start to rush because I got a signal that I'm out of time. I go through this implementation, how we did what we had to do to go from the old infrastructure to the new infrastructure while customers are still working. So what you might ask, how does it scale? Yeah? For the actual is real simple. If one edge is full, if you have no interfaces left for customers, that put another switch beside, connect it to the core, and then you are done. The only thing you have to remember what you try to do is, if you operate an IXP, you try to keep as much traffic as possible on the switch, because then it's only switched on the bus. And here is what you see. If you only have one switch, then 100% is local traffic. You have the two switches, the probability that it goes to the other switch is 50%, and so on and so on. As you see, the more access switches you have, the worse is the ratio of traffic being local. So the idea is, if you want to keep it local, use bigger switches as well in the edge. And for the core, it's the same. If your core switch is full, just put in another switch. And with this active and standby core, it's really easy. So you just first replace your standby core and put in a bigger device, and then you do a failover to your bigger core, then replace that standby, and then you are done. Test it, and then you are done. If you can get bigger switches, then what you do is you might what I call stacked core switches. Actually, that means, as I told, all of the edge switches are connected to the core by Ether channels. You split up the Ether channel. That means you put half of the channel on one device and half of the channel on the other device. You can only do it with a static Ether channel configuration, because then these both boxes are not talking to each other. Okay? And in that way, it really scales. That means you can have here an Ether channel of up to 32 if you go with the boundary, or 16 or whatever. That means finally you end up with an edge connected to, let's say, 16 switches in one core with just a single fiber. That way, this whole thing will scale for a capacity of well over 50 terabit. We are currently shipping 500 gigabit. That means this setup is really safe for the next at least 3 years, 4 years, 5 years. Because traffic is doubling, and 500 then comes 1 terabit, 2, 4, 8, and then finally, hopefully, we will have 100 gigabit, and then the whole play begins again. So that means building resilient, scalable, and high bandwidth IXP is possible, and it scales even to more than 40 terabits with the current technology. That means with switches able to have 128 gigabit, 10 gigabit ports, and